In this video, I'm going to talk about the generation of electricity, and it turns out that it's what we call an alternating current, and we'll get to why that is in a moment. So this is a diagram of a really simple AC generator. And so a generator, of course, is a device that generates electricity. It's converting kinetic energy into electrical energy. And what I've written here is electricity generation happens by rotating a coil of wire in a magnetic field. So we actually have to go in here and physically rotate this coil of wire, and then we'll get electricity out of it. Now, how do we rotate these coils of wire on a big scale, on an industrial scale? We might use hydroelectricity. In hydroelectricity plants, we use basically water, which spins a turbine, which causes this, this kind of coil to rotate around. We might use steam in a coal power plant to turn a turbine, which allows these coils to turn in a magnetic field. Now, I'll just point out here, these things in black that I've drawn here, this is called a slip ring commutator. And what that allows is, and it's a bit hard to tell here, this ring here allows this side, this wire coming off this side of the loop, to be attached to this side of the circuit. And we've gone here and we've drawn a light bulb here. And then this loop is always connected to this side of the circuit, and it's connected through a little brush here, and it connects to that side of the circuit. And so the same wire is always connected to the same part of the circuit, even though the loop is rotating. Now back to electricity generation by rotating a coil of wire. So how does this happen? Okay, this happens, or how do we get electricity out of it? Because of induction. So you can either think of it as you have a flux through the loop, which changes as the loop rotates. That's one way of saying it. Or the current is induced in those wires on the side as they cut through the magnetic field. Now, I'm not going to go into that in a great deal of detail in this video, because we've done a lot of work on seeing how those currents can be induced. So you can actually go through this and try and figure out which way the current will be induced depending on which way that loop is turning. And I suggest you do that to kind of help consolidate these ideas. All right, so how does the flux change with time? Well, we know with this rotating coil, if we're rotating it at a constant rate, it has a sinusoidal form. All right, and we could write an equation for flux. We can say the flux is the number of loops times the magnetic field times the area of that loop times the cos of the angle between the normal to that area, that loop, and the magnetic field. And we've been through that before. And then we could put that in terms of the rate of rotation, so the angular frequency at which it's turning. And I think I'm just going to, so that's the flux. I'm just going to take away those n's, because actually in our definition of Faraday's law, we've included that number of loops in there. So we'll just leave that for later. Now the EMF is the rate of change of flux. And I've written d phi dt here instead of delta phi delta t. And so this is a more proper way of writing it, but don't get too worried. You could just replace those with deltas if that helps you. In this case, though, because we've got a constantly changing flux, we really do need to look at or understand that that's the slope of the flux curve. And if we now have a look at what that d phi dt is, substitute that in there, we can differentiate the expression for flux, which is BA cos omega t, and we find that the derivative of cos is a negative sign, but then our negatives cancel. Work through this at your own pace, and you'll find that it's nBA omega sine omega t. And so if we look at the form of that equation, the form of that EMF, it is a sine curve. If flux started off as being positive at the beginning, like a large flux at the beginning, and reducing, then we would get a cos curve for the EMF. And of course, that's the same expression as for the current. It's the EMF and the current both have the form of, the sine function there. And I'm just going to write in there those maximum values. Oh, you can barely see, I'm very sorry. E0 or I0 corresponds to that maximum there of the EMF or of the current. And I'm just going to write that in here so that those final expressions would be some maximum value for the EMF times the sine of omega t, and the maximum value for the current times the sine of omega t, where omega is the angular velocity that is changing, so how many radians per second it's moving through. Okay, and that's what we're looking for. We're looking for the expression of how EMF and current changes through time.